All right, let's get started. PS10 is out, and it is due Monday. But remember that the TA hours aren't optimized for Monday due dates. So if you think you're going to need a lot of help, I'd get started right away so you can go to the K-Lab on Wednesday and Thursday to get.
Sorry, what do you refer to? What is, okay.
And then PS12 will come out, and PS11 rather, the final project will come out Thursday. And the first deadline will be the Wednesday before Thanksgiving. Then you need to either tell us who your partner is or tell us you're not going to have a partner. So at least be working on that. Nothing else is due before Thanksgiving. Are there any questions or problems about anything? Yeah?
So if we have like 8 days to use, then
Oh yeah, if you have a late day to use, you can use it. You can turn in PS10 on Tuesday. Yeah. Yes? Okay, the second deadline for PS11 is at the end of the week after Thanksgiving. And what you got to do is meet with the TA, schedule an appointment with the TA, and demonstrate progress. And I'll define progress later. And then the following week on Thursday, the last Thursday of the semester, is when the PS11 is due. I've learned through hard experience, if I give an assignment and give you 3 weeks to do it, you won't start until when you usually start, which is too late. So that's why I have checkpoints to make sure you're making progress. Okay, so we're going to continue talking about polymorphism, but first I want to talk about the mobiles that you did for PS9, and I want to just go over it and look at the solution. So here it is, and I'm going to scroll past the code I wrote. Okay, so let's think about this. This is supposed to return the weight of a mobile. And in all these examples, I have the base case correct, and the recursive case is just a stub. So what I told you in the write-up is that you can implement all of these with a single return statement here and here in each method. And the base case is pretty easy. If it's a bob, you just return its weight, because every bob has a weight. Trying to add up the weights of all the bobs. Now, down here, when you're trying to come up with what goes there when you're dealing with a rod, I think a lot of people think, okay, I've got to add up the weights of all the bobs in the mobile, because that's what it says in the comment. But if you think that way, you won't find a solution very fast. You've got to describe the solution differently. So instead of saying that this method needs to add up the weight of all the bobs in the mobile, how should you think? What's the structural way to describe the problem? What are you adding up? Okay?
Adds up all the weights on the left and all the weights on the right.
Okay, so he said it adds up all the weights on the left and all the weights on the right. I'd leave out the S and just say it returns the weight of the left mobile plus the weight of the right mobile. Okay? Don't worry how it's structured. You have a method that'll tell you what its weight is. So we just return left dot weight plus right dot weight. Okay? Recursively determine the weight of the left mobile. Recursively determine the weight of the right mobile. Add them together. Return the result. Okay? Hopefully you all did it this way, but I saw a lot of, at least attempts, that were not really close to this. Yeah?
You go ahead and use this on all your things there, is that fine? Like,
okay, so he's asking, can you say this dot is Bob, this dot weight, this dot left, this dot right? That's fine. Or leaving them out is fine as well. Now, I had a number of questions of the form. You know, people would, look at this base case and they'd say that can't be right. Returning the weight of the bob can't be right because that ignores all the other bobs in the mobile. And the mindset seems to be that whenever the return is executed in the weight method, then the the whole computation is over. That somehow what's returned to the base case is going to be what's returned at the top level. Okay, so what happens to this value that's returned right here when you work your way down to a bob? So let me get this picture right here. So let's say we come all the way, so we're trying to get the weight of this mobile. So we recursively try to get the weight of that mobile, this one here. Then we recursively try to get the weight of that mobile, and then we try to recursively get the weight of this mobile, and then we recursively get the weight of the bob. And we return 20. But what happens to that 20? Yeah? Right, so what he said was, okay, this thing right here, this rod right here is trying to compute its weight. And so it asks the left mobile, what's your weight? It gets back to 20. So it's waiting for that 20 to come back. Then it will ask for the weight of this mobile, and it'll get back 30. Then it will add the, not 30, the 5. It will add the 20 and the 5 and return 25. So at the point when we're calculating the weight of the bob, there are 1, 2, 3, 4 invocations of the weight method sitting on the stack, waiting for an answer. So the return statement in the call to the rod version of weight doesn't end all of those. It just ends the one call. So it's important to realize.
Rubbing on your shirt.
This thing is okay. It's really an aggravation. You try. Any better. Okay, so let's go. Is that working at all?
Yeah.
Okay. Okay, so there's weight. So I'd love to get questions from people that don't understand this. I know it's hard to do, but I can't fix misconceptions unless I hear what they are. That's no way to get a question asked. So. Okay, I'm going to skip that one for right now. Let's do the depth. So the depth of a bob, by definition, is 1. Otherwise, we got to find essentially the longest path from the root of the mobile to a bob. But someone else tell me, what is the structure way to describe what calculation this thing does when it's given a rod? How do you determine the depth of a mobile that is a rod mobile? Yeah? Okay, so we need to find the max. You compute the depth of the left mobile, the depth of the right mobile, take the max, and then what? Yeah? Add 1. So we find the depth of the two mobiles that are below us, take the larger of the two, and then add 1 for the rod, the extra depth that we're adding by the rod. So let's just return 1 plus. Okay. So the key is to describe the computation in terms of the structure of the mobile. You've got to describe the depth in terms of the depths of the two submobiles. You describe the weight in terms of the weight of the two submobiles. So you get this natural, a recursive call to the left, a recursive call to the right. Recursive call to the left, recursive call to the right. And that's consistent through all the solutions. All you have to do is figure out how to combine them to produce the overall answer. Okay? What about bob count? You've got to find how many bobs there are. Now, how's that different from figuring out what the total weight is? me put it another way. When would the total weight be the same as the bob count? Yeah?
All the bobs in one.
Okay, if all the bobs had a weight of 1, then that would be the bob count. So let's just do that. I'm going to change this to bob count. And that's all that takes. Okay. Number of rods. Well, if you're a bob, there are no rods there. Otherwise, how do we count rods? Let's hear from someone new. What's the structural way to do it? Yeah.
We do right rod count plus left rod count plus 1 for the rod you're counting.
Right. Oops. Wrong one. So she said we got to do how many rods are on the left in the left mobile plus the number on the right plus 1 because we're a rod. Yeah.
You put bob counts in front.
Easy mistake to make. Okay, so you see where we're headed. So let's go back to is balanced. I think that was the most involved thing. Yeah?
I found a rule that the bob count is always, the rod count is always bob count minus 1. Is that correct?
Okay, so he's observing that the rod count is always the bob count minus 1. Yeah, I think that is a fact because it's sort of a property of binary trees. One way to remember it, if you can't remember it exactly, about half of if you think about all the nodes in a binary tree, about half of the nodes are leaves. In fact, one more than half. Okay, so how can we tell, okay, what we got to do is balanced here. So the first thing that has to be true is that if we're in this case right here, we're dealing with a rod, we got to make sure that rod is level. So how do we decide the rod is level? Yeah?
The length of the left side times the weight of the left side equals the right length times right weight.
Okay, so it's I think what you said was it's the left length times the weight of the left mobile has to equal the right length Okay, so that will tell us if the rod is level, if the torques are the same on either side of the rod. And notice we're calling weight, which we defined earlier. So we're making weight, which will determine the weight of the two submobiles. But that's not a complete solution. What else do we have to add? Yeah. Okay. So what she's saying is that tells us the top level rod is balanced. We've got to decide if all the other rods are balanced. And the way we do that is we ask the left mobile if it's balanced. So that's what we do. 3 conditions have to be true, so I just AND them together and return the result. Okay? So I'm going to stop there unless there's a question about a particular method.
Don't move on yet.
Yeah?
If we didn't do it in one line, will we get posting on?
No, if you didn't do it in one line, that's okay. I know that even after all this time, a lot of students would rather use if statements, nested if statements, instead of ANDing things together. That's okay. Yeah?
Can we do longest rod?
Longest rod? Okay. Okay, we're supposed to return the longest rod in the mobile. If it's a bob, it just says return 0. Okay? So, who could tell me? ideally someone who hasn't spoken up yet. What's the approach to this? Yeah. Okay. So there are three things that we have to compare. There's the length of the current rod. There's the longest rod in the left mobile, the longest rod in the right mobile, and whichever is the largest wins. So we need to do a three-way max, but I only know how to do a two-way max. So that right there is the length of the current rod. And then we also need, and the second parameter is going to be the larger of. Yeah. So we return the largest of those three things. Left dot length plus right dot length, and the longest rod in the left, the longest rod in the right. If we had a three-way comparison method, it'd be a little bit simpler. Any other questions? Yeah.
Is there a way to short circuit a recursion in the same way that you can have like a break statement?
Okay, so the question was, is there a way to short circuit a recursion the same way there's a break statement in a loop? So, no. I mean, you can short circuit the current return from the current call, but like to return out of the top level of the recursion, unless you throw an exception, you've got to return all the way up. Any other questions? Yeah.
What about heaviest bob?
Okay. Heaviest bob. So clearly, if your mobile is just a bob, then the heaviest bob has the weight of the bob. Otherwise, how are we going to, what's the structural way, the recursive way of describing the heaviest bob in a mobile? Okay? Right, we have to find the larger of the heaviest bob on the left and the heaviest bob on the right. You take the larger of the two answers, and that's going to be the heaviest bob in the entire mobile. Okay, any other questions?
For you go back up to weight.
Any other questions? Okay. What I'm going to do next is I'm going to take this mobile example and I'm going to completely rearrange it. So let's look at the mobile class here. What is kind of weird about these instance variables? Yeah.
They're only initialized depending on the first Boolean.
Okay, so they're only initialized depending on this first Boolean. And that's exactly right. If our mobile is a bob, then we store a value in weight, and we don't care about left length, right length, left and right. We don't even touch them. On the other hand, if is bob is false and we got a rod, we don't store anything in weight. We use the other instance variables. So what I want to think about is having two classes, having a class called bob and a class called rod. Can you see a problem with that? Yeah.
Open has to have a mobile in it, so you couldn't put Bob in it if it was a different flag.
Okay. So, so basically what he said was, we got two distinct classes now, Rod and Bob, and we don't even have the mobile class anymore. So what should left contain? Should left be described to hold a rod, or should left be declared to hold a bob? Because it could be either. How do we deal with the fact that if we get rid of mobile and just have bobs and rods, that left could contain either one? Somehow we got to express that. Got an idea?
Yeah, we could have both of them subclasses of mobile.
Okay, so he's thinking about inheritance, having both be a subclass of mobile, whatever. But I'm going to do something slightly different. I'm going to make mobile be, so I'm going to make sure I'm using the right classes here. I'm going to have mobile be an interface. And I'm going to have Bob, the Bob class, implement the interface, and I'm going to have the Rod class implement the interface. And that way, if you create a Bob object, it's also a mobile object. And the same thing goes for a rod. A rod object is automatically treated as a mobile object. It can be used in any context where a mobile is needed. One thing an interface can also contain are constants, so I threw the formatting constants in here that are used to draw. So let's look at the methods. We have a display method. That's the method I wrote for you. Why is there no body? Why does this header end with a semicolon and no body? Yeah?
Because interfaces don't have a body, the method declaration.
Right, interfaces don't have bodies. They're just declarations of methods. So what this is saying is that anything that claims to be a mobile, must have a display method, a weight method, an isBalance method, a depth method, and so on. It must have these methods. So let's go look at the Bob class. So you see I said Bob implements mobile. So I had to put all these methods in there. You see them all there. Okay. There's the display method, which I don't really care about. So every Bob object contains a weight. So there's only one instance variable now. So okay, so let's look at the methods. We ask the weight of the Bob, we just return weight. We're asked, is a mobile balanced? We say yes. Is a Bob balanced? We say yes. What's the depth of a Bob? We say 1. What's the Bob count of a Bob? 1. What's the rod count? 0. Where did these returns come from? Yeah? They came from the base cases of the old version. Okay? Then there is the rod class, which also implements mobile. It has these instance variables, these 4, which matter. It has, well, the display method I wrote for you. And then the weight method returns the sum of the left and the right weights. The isBalance method does that thing that we wrote before. Depth, Bob count, and so on. Where did these returns come from? They came from the original recursive case. Okay? Now let's look at the constructors. Okay, we have a constructor to create a rod. You just pass in the left length, the right length, the left and the right. Left and right can be mobiles. Okay? So what that means is you could pass as the parameter to rod either another rod object or a Bob object, because both are mobiles. Same thing for right. And all this constructor does is save them away. It's the same as our old constructor, except we don't have that isBob method, but isBob variable anymore. If we look at Bob, there's one instance variable, which is the weight, and then we have the simple constructor that just records the weight. If we look at this one here, notice I want to compare with, so this is the original mobile example. So we were either calling to create a rod, we called the 4-parameter constructor. To construct a Bob, we call the 1-parameter constructor. Now, we just either call the rod constructor or the Bob constructor as necessary. Okay? Otherwise, you know, it just took refactoring the code, moving the code around and reorganizing it in different ways. But I want to ask you a question. Let's say we make mobile 1 right here. So M1 is that mobile we looked at before. If we pass M1, if we ask what is M1's bob count, which bob count method is called? The one in the rod class or the one in the bob class? Right? There are two bob count methods. So we got one there. We got one here. You take a mobile object and you call the bob count on it. Which method is run? How does Java know which method to run? Before there was just one method. How does Java decide which method to call? Yeah. Well, yeah, we got override here, but we also got override here. Yeah.
Depending on whether the method was called on a rod or a bob.
Okay, so he said it depends on what the object is. So if you have a rod object, even if it's stored in a mobile variable, you say, give me the, in fact, let's go right here. There I have a, notice when I create a rod object, I store it in a mobile variable. And M1 is a mobile variable. If I say M1.bobCount, what Java does is it looks at M1 and says, yes, declare to be a mobile, but it looks at the actual object in it and says, that's a rod object. It was created with a rod constructor. Therefore, I'll call the bob count method from the rod class. On the other hand, if you had a variable that contained a bob object and you called bob count on it, it would call the bob count method in the other place. So Java's doing that if else for you. It just looks at what kind of object it is and calls the appropriate method. So that's kind of nice. Now I'm going to show you something else kind of neat, but before I do that, I want to pause to help with any questions you might have. Yeah?
Is there an advantage to doing it through an interface like this rather than making the whole extension of all of that?
I didn't hear the last part. So you're asking, is there advantage between doing it this way and doing it what way?
And using inheritance, saying that rod and bob extend.
Okay. So he's asking, what's the trade-off between implementing an interface like I did here, or creating instead of having it extend a class. So if I'd made mobile a class instead of interface, I could have extended it. Okay? Well, what would this class look like if what would it look like if it were a class instead of an interface? What would we have to change about it? Nothing.
You have to give it all the bodies.
We'd have to implement all the methods. So I would have to implement depth. And how would I do it?
You have to use the if-then that you used before, right?
Yeah, you would have to do something like this. You would say, if this is an instance, I haven't talked about instance of, but you'd have to say, if it's an instance of a bob, do one thing. You'd have to cast it to be a bob, and then, well, no, you wouldn't have to do that, but you'd be back to the if else. So if you think about having a class, you've got to have some code you want to write. If all you want to do is declare methods, declare that any mobile has these methods in common, use an interface. If you know how to implement some of the methods, then you use a class and you inherit from it. We'll look at these trade-offs more next time, but yeah.
So would it be considered better practice to use one version of the other?
Okay, so now we're comparing the way I'm doing it here with an interface and two classes with the way I had it before, which was one class with the conditionals. And people argue about that. So either way is okay. But there's a neat thing about doing it the way I did in the second case. And that is, it helps, there's a certain kind of, the thing is programs don't always stay the same. They change over time. So can you think of a change to the definition of what a mobile is that would make it easier, where it's easier to use this interface approach than the other approach? Yeah?
There's more than two things coming up.
Okay. He said if there's more than two things coming off a rod. And what I had in mind is you could invent a new kind of thing that could be a mobile. So maybe instead of having a rod with two mobiles hanging off, or a bob, you could have a third one, which is a rod with things hanging from either end and one hanging from the middle. A tri-rod. Now, what would it take to add tri-rods to the version of the program we have right now? All we would do is we'd create a new class called tri-rod, which would implement the mobile interface. And we would implement each of these methods in there. But we would not have to touch any of our code. We would not have to touch the rod class. We would not have to touch the mobile class. We would not have to touch the interface. We would just plug in a new implementation of a new class that implements mobile, and suddenly everything would work together correctly. Now, what would it look like if we made that change to our original program? This class right here. So what would happen if we had to add a third kind, a tri-rod? Yeah. Okay, so we would have to have we would still have left length and right length, but we'd have to have left, right, and middle. So we'd have to have another mobile object in there. Up here with is Bob, we'd have to have is tri-rod or something like that. And now it gets worse and worse that you create a Bob object, you've got even more useless instance variables floating around. And then after you've done the instance variables, you'd have to add a constructor to this class. And then you'd have to come down to all the methods. And now it would be if, else, if, else. If, else, if, else. You'd have to change all that. The cool thing about using the interface is you just have to add the new implementation of tri-rod, and you don't have to change anything else. And the new classes work together correctly. Now, I don't feel like implementing tri-rod. I'm going to do something else. Let's implement a red bob. So red bob, I'm going to say, works just like a bob, except it's red. That's the only difference. All right, so I want something that's just like a bob, but it's red. So when you hear that, I want a class that's just like this other class, but slightly different. What form of polymorphism should you be thinking about? Inheritance. So in the old days, before there were such things as inheritance, what you would do is you would copy the code for Bob, call it red Bob, and then go change it a little bit. With inheritance, you don't have to do that in a text editor. You can do it in the language. So let me show you how that would work. So I'm going to add here to mobiles, I'm going to say create me a new class, and I'm going to call it red Bob. And there it is. I want it to extend Bob. Okay? Let's see what it's complaining about here. Okay, we've got to have a constructor. So that would be public what should we do? We're constructing red Bob to have a weight. Do we want to store the weight in an instance variable here? See, I don't want to rewrite all those methods that you wrote for your assignment. A Bob is just like a red Bob, so what should we do?
Do you just call super and pass it the weight?
Right. Remember, a red Bob is still a Bob, so that instance variable is still floating around. It's just inaccessible to us. So we call the super is calling the Bob constructor, basically calling the Bob constructor and telling it to store this value weight as its weight. And it will use that value when the inherited, will use that value indirectly when the inherited methods run. Now, what do we need to change? If we just did that, there's really no difference between a bob and a red bob. What do we have to change? Yeah? Right, we have to change something that deals with the color. So let's go to Bob, and let's look at its drawing code here. So you'll see that it does this displaying here. So we need to override the display method. Okay, we're going to change the display method so it draws in red instead of drawing in whatever color it's using now. So I've taken Bob, I'm going to go to red Bob, I'm going to paste this in. So we're overriding the display method that we inherited from red Bob. And we got a problem. Weight, and we can't access the weight here. I need the weight and I can't access it. So let's do it a different way. What I'm going to do is I'm going to say, okay, I'm going to change the graphics context so that it draws in red. And then I want to call the old method that I just overrode. And that's done by saying super.display. Okay, so what I've done is I've extended Bob to red Bob. I wrote a constructor to save that weight away in the instance variable we inherited. And then I just changed display, overrode display, so that it sets the color to red before it calls super.display. Before it calls the original version that needed to access the instance variable. Now, got a question here.
Someone asked, how can you tell if it's a class or interface?
How can you tell if it's a class or interface? It says right there, red Bob is a class. Mobile is, well, I'm looking at the wrong one there. Is an interface. It's just declared. Public interface or public class. Okay, back to red Bob. How can we test this out and see if our Bobs are red? Well, we've got this guy here. We could run it and see what's drawn. Okay, nothing in red. Yeah?
Change one of your bobs to red bobs.
Yeah, we need to be constructing, I'm in the wrong class anyway.
Yeah.
Got to be careful here. This is the modified one. Right, so let's just make this one here be a red Bob. So notice I didn't have to change, red Bob's a perfectly fine mobile because it extended, it implements the interface. Red Bob extends Bob and implements the interface. So let's try running that. And there you are. So all we had to do, was this red before? So maybe we have a slight bug, maybe after drawing, set it back to black maybe.
Actually, doesn't display everything?
Yeah, I'm not sure why everything was in red, but let's do that. Okay. So we just get red what we wanted. And this is all we had to write. Basically, we just had to customize the display method. Now, if later on, one of you decides, that display method back in Bob could be done better. Maybe you want to change something about it. You change it. I'm still calling the thing you just changed. So the exchange is also inherited, the change is inherited here. So the cool thing about inheritance and interfaces is you can have a working system and you can plug a new component into it without having to disturb any of the rest of the system, and it still plays nicely with it. Okay? Any other questions about this? Okay, now when you're working, the current assignment, you're doing a lights out game, graphical user interface. So the next thing I want to do is going to have two purposes. One is I want to show you, I want to go through the implementation of the Connect4 graphics part that you didn't implement. And for two reasons. One is to show you how it's put together, which will help you with your assignment. The other reason I want to do it is to point out more uses of polymorphism in there. So let's take a break and we'll do that. Okay, let's get started again. As a reminder to those of you watching live elsewhere, if you can ask a question by commenting on the video, and Stefan will try to notice and ask it for you so I can answer it. Okay, so Connect4 you're familiar with. It has this button to create a new game. You click in columns and pieces appear. And when you win a game, that happens and you get credit up here. It says wins won. And then you start a new game and it's yellow's turn to go first. There's also these indicators that switch back and forth up here. Tell you whose turn it is. So that's the graphical user interface. What you wrote was what I call the model. You wrote the code that didn't know anything about graphics, just knew about the state of a Connect4 game. And that separation of a program into its view and its model is a good thing. What's good about it? Why is it good to separate out, to have one class, one object that represents the state of the thing, and another object that just deals with interacting with the user and displaying things? Yeah? Okay, she said for testing. So it's, once you have a game like this, it's a little hard to write a unit test against the graphics. There are ways to do it, but they're complicated. So what we want to do is make as much of the program testable as possible. So we put all the smarts of the game into one class, one kind of object, and that, so it's testable. And then hopefully the user interface code is simple enough that, that we can get it right, or we just have to resign ourselves to testing it manually by playing the game. Now, there's an acronym, MVC, for Model View Controller. And that's a further elaboration where the model is the smarts, the view is what the user sees, the controller is what connects the model and the view. So it's the controller that notices, that button has been clicked, I need to do this to the model and then do this to the view. And I haven't broken that out. In the Connect 4 game, where's the controller? Where's the part that notices the user has done something and then calls methods in the controller and the view to deal with it? Did you put that code into the model? No. It's in the view as well. So in a more faithful rendition of model view controller, there'd be a third class. But I guess I felt that was overkill for a game this simple. And people always ask me, when you implement your lights out game, do you have to have, I guess I said in the directions to have a model view, have a model class and a view class. And I would prefer that you do it that way for testability reasons. Okay, now look at the view up there and tell me, how is it, you've looked at a few GUIs now. What are the pieces? When we look at the code, and we're going to look at the code and tear it apart, how do I get it to look this way? Yeah? In the back, yeah?
At the bottom, there's a button for
Okay, so this is a button right here. So that's a button object, J button. Yeah?
Looks like the biggest J panel is just a border.
Okay.
Without east and west.
Okay, so we said the main J panel here that forms the window is a border layout where this stuff up here, the winds, the ties, the winds, the move indicators, are in the north. So there's a skinny J panel that has those. Then there is a J panel that has the new game in it. That's at the south. And then the center, which is the rest of the real estate. So if I enlarge this, the center gets all the extra space. That's the center of the border layout. Then how do these circles or these ovals now get laid out? In that nice grid, yeah.
Grid layout.
Right. So there's a grid layout of the J panel that's in the middle. Now, what about these individual things here? These circles. What are they?
Panels.
What'd you say?
Panels. J panels.
Okay. He's saying maybe these are J panels. And in fact, they are. But when have you seen a J panel that looks like a yellow circle? That's something we got to figure out. How do we arrange? There are a bunch of J panels arranged in this grid, but somehow they appear not as sort of blank things. Because normally a J panel, like this big J panel that holds these, is basically a blank blue space that has things put on top. So we got to figure out how to make these things appear. Same thing for this, this circle here that goes back and forth as people move. That's also a J panel, and it's pretty much the same thing as these guys, just smaller. What kind of layout do you think's up here? It's got something on the left, something on the right, something in the middle. Yeah?
Is it another border with an east, west, and center?
He's saying it might be another border. I don't remember, to tell you the truth. It might be a box layout, a horizontal box layout. I don't think it's a flow layout. We'll see. So given this discussion, when you go to design your view, for your lights out game. What I suggest you do is just try to draw it out on paper what it's supposed to look like, and then figure out what layouts you need, what J panels you need. Then you know how to put it together so that it looks right. So let's go and look at it. So we go to C4 board here. No, that's what you wrote. C4 display. So I put a lot of constants up here. Colors and strings that are displayed, and rows and columns, and the width and height of the window, the font size and all that. Why is it a really good idea to define all those as constants in one place? Yeah? It makes the code readable, is what he said. Because if you see height somewhere down here in the code, you'll know what it is. If you see 600 down there, you don't know, why is it 600? What does that stand for? So one reason is you name the constants. The other reason is you can change them easily. If you want the width to change, you just change the 600 to something else. On the other hand, suppose these weren't here, and instead all these constants were dispersed through the code. Suppose you decide you want the width to be 800 and the height to be unchanged. Could you do a global replace of 600 with 800? If you did that, you'd be changing the height as well. Or even worse, maybe there's a 600 in there for some other reason, and you change it to 800 as well. So don't use magic numbers. Don't put numbers directly in your code. Put them somewhere, give them a name, and so they can be changed. Now I want to point out, this is the convention in Java for constants. Uppercase, separated, where words are separated by underscores. Don't just use this and decide that all your instance variables will be done the same way. That's not the style. Only constants get the uppercase treatment. So let's look at what this class here is called C4 Display. So let's see what it contains. It contains a reference to the model. Because when things happen on the interface, we have to make method calls on the model. So we got that. What are these are? P1 indicator and P2 indicator. Where do they show up in the window here? What are P1 indicator and P2 indicator? Yeah, that right there. That red thing is P1 indicator. That's P2 indicator. So it's a move indicator object. That's something I wrote. So move indicator is not a swing class. It's something that I wrote. Okay? We have a J label that is called P1 wins. That's this 0 right here. And P2 wins. That label right there. I think it's the wins, the colon, and the 0, actually. Number of ties is another J label. And then there's a board class, which is this thing right here. And that's a class that I wrote as well. So let's see what's involved. So a C4 display, here's our first look at polymorphism in this case. A C4 display is a JFrame. It extends JFrame, so it has all the JFrame methods. And it implements action listener, which means we can use use C4 display objects to listen to buttons and such. So we set the title. This is important so that when you X out, it actually ends the program. So you just put that in. We set the size appropriately with our constants. And we start laying things out. We create the center portion, the north and the south, and put everything together. And you've seen that before, so I'll sort of go through it quickly. We got to have an overall root panel with a border layout, and that's the content pane for the J panel. So for the J-frame. We create one panel which has it's a J panel. It has a background color. It contains the wins, the ties, the losses, the indicators. And I did not set a layout for it, did I? So it's a flow layout. Surprises me. Oh, I see one. Oh, okay. Haven't looked at this in too long. scores is the top portion that contains all the scores. It has a border layout, as you suspected, and we add it to the north of the root. Then this panel just has player one stuff, and it's added on the west end of the scores panel. Ties goes in the center. That goes in the east. So that's just a hack to make everything lay out right. Then we create the bottom portion, which has that button, and then we somewhere we created a board object and put it in the middle, and then we refresh the display, set it visible to true, make it visible, and we're off. So that's what the constructor does. So when you actually run the program, it calls the constructor, and that shows up. Everything got laid out and displayed. So what I have here is a model you can follow when you do lights out. Your constructor needs to do the layouts, create all the objects, save them to instance variables if necessary. Okay? So any questions about the constructor there? That's where most of the code is in the view, because it's got the constructor has to lay everything out. Okay. Let's look at the board. So where are we? Right here. We created a board object. So I called the board class, created a board object, and I put it in the center of the root. You got a question?
Yeah, one thing about your constructor, I noticed you use like a refresh method instead of using pack. Is that kind of normal? I was expecting to see pack somewhere basically, and I didn't see it.
Yeah, let's go look at board.refresh. Yeah, it doesn't seem to do pack, which worked this time. So I tell students I have superstitions about pack. Sometimes it seems to be necessary, sometimes it isn't. In this case, it seems to work without.
If you like tack it on there, would it still work, or like?
I think so, yeah.
Is this not necessary?
Yeah, I don't fully understand what pack is for.
Yeah.
I put pack in the Minesweep program and it just ruined it.
Yeah, so Stefan just said he put pack into his Minesweeper program and it didn't work. So if it's not working, add pack. Or take it out, one or the other. Okay, so let me go back up to the board. Right here. So there's where I create the board and I add it to the center. So board is a class that I wrote. It's down below in this file. What kind of object does it have to be if we're going to add it to our root? Yeah.
J-panel.
It has to be a J-panel or something similar. But it's a class I'm writing. So how am I going to arrange for board to be usable wherever a J-panel can appear? How do I arrange that? Yeah? Right. I make board extend J-panel. So let me come down to these. I should mention these methods are just methods that do various things. That set the view so that it's P2's turn to move, or that it's P1's turn to move, or that it's when the game is over you do that. So that's called in response to user actions. So those are simple methods. This is called when the new game button is clicked. So there is another instance of polymorphism, because we implement the action listener interface, so we can register as an action listener, and this method is called when the button is clicked. So we can make a new, start a new game and refresh. Okay, here's the board, the central portion where the circles are. And you can see that it is a J-panel, and we're also going to make it a mouse listener. Okay? When we create the board, we pass in a model object, that's the smarts, and the display. So we record them away. We set the background layout, we set a layout, we set a background color, and we create a whole bunch of square objects and add them to this panel. So what's happening here is we are looping through all the rows and columns, For each one, we create a square object. We tell the square its coordinates in the board. We add a mouse listener to that square. So whenever the square is clicked, the board object to be notified. And then we add, the add method is something we've inherited, we add it to the board. And that's all possible because a board is a kind of JPanel. So once we've added all those, I don't know how many there are, 42 different squares, those circles, in the, to the board, they lay out a nice grid because we set the layout to be a grid layout. So that's what makes them lay out all right. Now, what are we going to have to add to the board method, the board class, besides this constructor which lays everything out? What other methods do you expect to find down there? Well, we're going to have to implement the methods of the mouse listener interface at a minimum. So let's go see what's down here. So there's the refresh. The refresh is the method that we called from the other class, but it's called whenever we need to just display everything. And so it loops through all the squares and figures out where the square is and sets colors. This just updates everything about the display and then asks for it to be repainted. So repaint's a method you can call whenever you want something to be redisplayed on the screen, you call repaint. So this code just sets everything up, sets all the indicators to be the right color, and then calls repaint. Okay. These are the methods that deal with mouse clicks. So when the mouse is clicked, we don't care. When the mouse is released, we don't care. When the mouse enters, when the mouse exits, we don't care. We just care when it's pressed, so when it goes down. So let's look at that code. That's sort of some custom code we're putting in this class. So what's happening here? We know that the J panel has been clicked. The board has been clicked. So what is get source going to be? Yeah. Right. The thing is actually being clicked. Someone's trying to click on the board, but the board is covered with squares. And so whichever square was clicked is going to be the source. So we obtain the square that was actually clicked. What do you suppose that method does? Okay, it gets we can look at the Java doc. Get the column the square is in on the board. Okay? We do a refresh operation and find out, the result tells us whether someone won or not. So basically, we tell the model, put a move in that column. We find out what happened. Now the model has changed, so we call refresh so that the view looks like the information that's in the model now. And then we display wins or ties or nothing, depending on what the result of the move was. So this is where a user action, pressing a button, makes a call to the model to update itself, and then a call to the refresh method which takes information from the model and updates the display. And when that's all done, we do one more tweak. We display if there was a result. So that's where all the action happens in the game. That's when stuff is clicked. Every time you click anywhere on the board, any of those circles, this is what's causing things to happen. And this is the code that something happens, we make a call to the model to update it, and then we refresh our display. Okay, now, we go up to the squares. We're creating squares and adding them to the J panel. So what kind of thing does a square have to be? Yeah? It's not a button. Yeah? It's a J panel. But it's a J panel that looks like a circle, a colored circle. So let's see what happens. So here is my square class. It extends J panel. Every square knows what row it's on, and what column it's on, and what color it is. So when you create a square, it has a row, it has a column, and it starts out being the background color, which means it's invisible. If you have a square, you can ask what row it's on, you can ask what column it's on, and you can set the color of the square. And all that's nice. Well, what's it going to take to make the square show up as a colored circle? How are we going to make this J panel different from all other J panels? So it looks like a red circle or a yellow circle. Because right now, a square is just a J panel that happens to have a couple of extra methods, 3 extra methods. What are we going to have to do to make it actually behave differently than every other J panel in the world? What do you think? If you want to change the behavior of something, what do you have to do? We're extending J panel. We want to change the behavior of it in some fashion. How do we do that? Yeah?
Override something?
We override something. We got to figure out what method is responsible for drawing the J panel and override it. Whatever it's doing now, we want to customize it. So that method is called paint component. And so this here is where we make the change. So we take the paint component exists in every J panel, knows how to draw the J panel, just draws a blank. So we're going to override it, and let's see what we're going to do. This thing here, these rendering hits, make the graphics a little sharper. So I'm just setting G to do that. I'm setting the color to be the board color. So basically, this method is called anytime swing decides that it's time to redraw this J panel. So it draws the entire J panel the color of the board, right there. And then it draws a circle in the middle of it. And so it overrides paint component and does that. So the cool thing is, the swing classes that you're using were written a decade ago. And those swing classes contain code that calls paint component. And by overriding paint component in the JPanel class, this new class we've created just fits right in, and when swing decides it's time to repaint, it calls the overridden paint component method. Now, what would happen if I changed the name of this? Called it paint component X. And why is it complaining? Yeah? Right. We say we're overriding a method, but there's no method called paint component X. So I'll comment that out. Now it's happy. How's my game going to work? What's my game going to look like? Anybody want to make a prediction? Yeah?
Just a blue square, right?
Yeah, it's just going to be drawn like any other J panel, so let's see. Well, actually a white square because we didn't ever set the color. So what happens is I'm moving. You just can't see what I'm doing. I want even. You can't see where I move because we're no longer, you know, we're not overriding component X anymore, paint component anymore. If I override it again though, it'll start working. So when we didn't override it, it's using the default method that is inherited from the J panel, which just draws a blank. Yeah? Okay, if you leave it as paint component but get rid of the override, the override thing is optional. It just protects you against making a typo. Yeah, it'll work now. Okay? This is here. The advantage of saying override when you mean to be overriding something is if you screw up and misspell it, you find out about it. Whereas without it, you wouldn't. And then that's a bug you have trouble finding. Okay? What would happen if I didn't do this part? So what I do is I take the square, I fill it with the color of the background, which is blue. And then I draw the oval, which is red or yellow. What happens if I comment out that fill rectangle method in the overridden method? Any predictions? What are we going to see? Yeah?
Would it just be like the order of it, just be the square, not the actual?
Yeah, the squares will still be that white that we saw, but there'll be the color circles in the middle. No? How does that work? Oh. Probably that color fill rectangle isn't useful. Let me do it this way. All right, I'm completely confused why that works. What happens if we do this? I'm pretty sure if I comment that out, it'll stop working. If we don't actually draw the circles, I'll be shocked if it actually displays circles. Okay. So we got the blue background now, but we don't have the circles. Okay, so that's just overriding a key method. Here's the move indicator class, which is also a JPanel. So those are just the things at the top that where it shows you there's moving, as little circles. So it's a JPanel. When we create it, we set its preferred size and its background color. We can set its color, and then the paint component method looks pretty much like the paint component method for the other thing. We just override the paint component. So if you want to have a custom thing that's like a JPanel but somewhat different, you just, if it's appearance you're trying to customize, you just override the paint component method. Now I want you to compare this with what it would have looked like if to obtain a move indicator, you had to take the JPanel class, copy it, change everywhere it said JPanel into move indicator, and then go and modify the repaint method. Okay? Because we can go, here's the code for JPanel. So we could have done that exercise. We could have taken this thing and copied it and changed the names and go find the repaint method. Let's see if there is one, if it may be inherited. Yeah, the repaint method is inherited. We don't even see it in here. What a mess. It's much cleaner just to say, okay, I know there's a JPanel class. I don't care about its code. I'm just going to extend it by overriding one of its methods. And now you get all the other behavior of a JPanel, but you customize its appearance. So those are the kinds of thought processes you're going to have to go through when you create the lights out. But you can use this as a model. Because actually lights out is a 5x5 array of lights, which you can do as circles. And you know, it's going to be structured pretty similar to this. And just to emphasize one final thing, where does all the user interface stuff happen? If you had to use one term to describe where in this class things actually happen in response to user actions, what would that be? So, where does it notice that a button has been clicked? And where does it notice, I'm sorry, that one of these circles has been clicked? And where does it notice that the new game has been clicked? That's the user interface part. What'd you say?
In the display class.
Okay, but specifically where does it notice the click has happened? Yeah. Okay, these clicks are noticed in a mouse listener. And this click is noticed in an action listener. So it's in those overridden listener classes, listener methods, is where all the user interface stuff is. And that'll be true for you as well. You'll have some sort of listener that notices when a button has been clicked or something else has been clicked. And what that has to do is make a call to the model to update it, and then change the view to reflect the updated model. Okay, any last questions? Yeah?
Your overridden mouse listener object, when you type
Yeah.
Where, how does Java know how to type where?
Okay. So we're looking for right there. So C is all we know. What this is doing is this method gets us all the components that have been added to the board. Okay? And all Java knows by default is those things are all components. That's what they all have in common. But we know better. What do we know about, we're the ones that added things to the board. What kind of things did we add to the board? When we built the board up here in the constructor, what were we adding to the board? Squares. The only objects that have been added to the board are squares. So even though, you know, when we say give me all the components that are on the board, and we start iterating through them, we know that that component right there has to be a square, because we're the ones that put it there. And so this is a typecast that says, treat this as a square. It doesn't change anything about the object. It does no conversion on it. What this typecast does is it checks to make sure this really is a square at runtime. So when the program is running, it'll take this component, make sure it's really a square, and then if it is, then it's okay to store it in S. If it's not a square, it will throw an exception.
So is that same thing happening in the mouse listener method that you have?
Yeah. The mouse listener knows that the only thing that could have been clicked on was a square. And so we're doing this to satisfy Java. And at runtime, it'll check to make sure it's really a square. Now, if other things have been added that weren't squares, then we get an exception. But we're not even bothering to cast the exception because I just know it's not going to find anything. So when you cast a float to an int, or an int to a float, yes, the data is changed. This type of cast is just a runtime check to make sure that this thing you think is a square really is a square. Yeah?
What's the difference between mouse click and mouse press?
Press is the down motion, released is the up motion. Well, hold on.
Well, right above it says mouse click.
Well, let's do a test here.
Clicked is both.
Yeah, click is down and up.
So I'm going to press and not release. So pressed is the down motion. So yeah, they're right. Clicked is a down and an up. So if I move this all, let's say I took this out and pasted it here, it'd be a very subtle difference. So I run it now. Now I push down and nothing's happening until I release. The problem was if I push it and move it slightly, it doesn't detect it as a click. You have to, so I'm pushing it down, I move the mouse, and then I release it, nothing happens. So, you know, click is like up and down on the same pixel, which doesn't seem like a good idea, so I'm going to change it back. Yeah?
I noticed that there's something called suppress warning serial. What does that mean?
Okay, so he's asking about at the top up here, suppress warning serial. Some classes, when you extend JFrame, some classes Java wants to have serial numbers, and so it's telling you here you need a serial number. I can define a default one like that. That's only important if you're serializing an object, which means turning it into something you can store in a file. We're not doing that, and I'd rather not see that. So rather than have to put that in, and rather than have to put up with the warning, I just say, I don't want this to have a serial ID. Don't bother me anymore. Okay, we're out of time, so if there are any other questions, I'm up here.